Okay, welcome back guys. Today we'll look at paper 1 variant 11 of the May-June 2023 series. Now as always, as well as watching this video, I would recommend checking the mark scheme, because while I might have like 2 or 3 answers, the mark scheme might give 4 or 5. Right, so the main purpose of these videos is really just to explain explain my thought process, and hopefully give a sort of more detailed explanation than what they give in the mark scheme. Right, so the first one then, binary is a number system used by computers. Tick one box to show which statement about a binary number system is correct. Right, so base 1, no, base 1, if you want the name, I guess that's going to be a unary system. Obviously, right, base 2, so this is going to be binary. Right, base 10, well, that's denary. And base 16, right, hexadecimal. Right, denary numbers are converted to binary numbers to be processed by a computer. Right, convert these denary numbers, right, to 8-bit binary numbers. So here, if we want, we can write out the positional values. So 128, right, then 64, right, 32, 16, 8, 4, 2, and then 1. So if we think 50, well, right, there's no 128s, no 64s. Right, so let's go 0, 0, right, but there will be a 32. There will also be a 16, right, that'll get us to 48. And then we just need 2 more, so then we're just going to have this 2 here. Right, the next one, again, no 128s, but there will be a 64. Right, then if we plus 32, that'll get us to 96. Right, then we just need, then we just need 6 more. So right, let's go 0, and then 6 is going to be 4 and 2. Right, okay, so the last one, right, so here there's going to be 128. There's also going to be a 64. Right, and if we think this will get us, 132, right, 192. And then, right, to get from here, I think, there won't be a 32. Right, but there will be a 16. So that'll get us from 192, right, up until, 208. Right, then, so an 8 will be 216. Right, and then a 4 is going to be 220. Right, then, no 2s, and then there should just be a 1. And this one we can also check, because if we think, if we have all of them, right, so all 1s, it's going to be 255. So here effectively, there's not a 32, right, there's also not a 2. So effectively, if we just do 255, and then we can say minus 32, and then minus 2, that should equal 221. And so this is going to be 34. And I think if we do that, right, it's 221. So that's just a way you can sort of check quickly. Right, binary numbers are stored in registers. Negative denary numbers can be represented as binary using 2's complement. Right, so just represent this using 2's complement. So here then we want to think, the first one this time is going to be minus 128. So there will be this, and I'll actually show you 2 ways to do it. And now we want to think, what do we want to add to this in order to get minus 78? So effectively we need to add 50, right? Because if we have minus 128 plus 50, that will get us to the minus 78. So 50, it's not going to be a 64. In fact, hang on. It's not going to be a 64. Right, but there will be a 32. Okay, there will be a 16. Right, there won't be an 8. There won't be a 4. Right, there will be a 2, and there won't be a 1. So I think that should be correct if I've not made a mistake. And again, this of course we can check, right? So minus 128, plus 32. So right, that's going to be, minus 96. And then plus 16, that gets us to minus 80. And then plus 2 is right, minus 78. Now this is one way to do it. We're just kind of directly calculating the value. Another way you can do it is where if, let's say, you calculate the positive, right, and then you just want to flip the bits and add 1. So to do that, 78, and again this is positive 78, there's going to be a 64, and then we just need 14. So right, that's going to be 8, that's going to be 4, and it's going to be 2. Right, so then we want to flip the bits. So flipping the bits, 0 becomes 1, 1 becomes 0. So let's just flip all of these. Right, then what we want to do is add 1. So let me just write down 1 here in binary. And this method is a bit more kind of quite a lot more long-winded, but possibly is easier, if you're not confident with adding like negative numbers. So what we want to do then, basically it's going to be these 2 numbers here. So yeah, this, well, this thing, right, and then also, yeah, this 1 here. Right, so if you look at this one, we've got 1 plus 1, so 1 plus 1 is going to be 0, okay, but then we carry the 1. The next one, well, 1 plus 0 plus 0, okay, that's going to be 1. Right, then we've got 0 plus 0, that's 0. Again, yeah, 2 zeros. Right, then 1 plus 0 is going to be 1. Again, 1 plus 0 is 1. Here's 0 plus 0, all right, that's 0. And then, yeah, 1 plus 0, right, that's going to be 1. And then if we look here, this is our answer. So yeah, 1, 0, 1, 1, right, so yeah, that's the same as this. And then yeah, 0, 0, 1, 0, which again, yeah, that's the same as this. So yeah, of course, this is correct. And when you've done your workings, of course, then just copy your answer down here, yeah, into this register, right, or answer box. Right, 2 8-bit numbers are given, you add the 2, okay. Right, so we just have to add these. So if we think, well, 1 plus 1, right, and I will just explain this. So if we think, if we have 1 plus 1, well, this will sum to 0, but then we have a carry of 1. And, some people get confused about this. Now, of course, if this is denary, let's say we have, 5 plus 7. Well, effectively here we're saying this will sum to 2, right, with a carry of 10. And, if you think, well, we can say 5 plus 7 equals 12, right, and, we can see that here because, well, we've got this 1 and then this 2. Likewise, in the same way in binary, okay, 1 plus 1 in binary, technically we can say, right, this equals 2. And of course, 2 in binary is 1, 0. And likewise here we can see this, right, because, yeah, here is going to be the 1, 0. Looking at this 1, and then, yeah, this 0, right, that's what gives us the 2. Similarly, right, if we had, I don't know, like maybe here we have, right, 1, 1, 1. Well, in that case, that's going to sum to 1, right, and then also with a carry of 1. And, this also makes sense because what we've got, well, 1 plus 1 plus 1 is going to be 3. And if we think, right, in binary, yeah, 1, 1 is going to be 3. And that's what we've got because, again, we've got this sum of 1, right, and then here we've got the, we've got the carry of 1. All right, so hopefully you're confident with that, and then let's just do it. So 1 plus 1, right, that's going to be 0, carry the 1. Again, 1 plus 1 plus 0, well, okay, yeah, sorry, right, that's going to be 0, but then carry the 1. Right, yeah, 1, 0, 0, right, that's 1. 0, 0, right, 0. Yeah, 1 plus 0 is 1. Right, 1 plus 1, again, that's going to be 0, carry the 1. And then, yeah, 1 plus 1, that's going to be 0 and carry the 1. And then finally here, right, 1, 0, 0, okay, that's going to be 1. Right, next one, it says 2 binary numbers are added by a computer and an overflow error occurs. Explain why the overflow error occurs. So basically overflow, well, that's when if we have a positive number, let's just say plus, right, so a positive number plus a positive number, and then if it equals a negative number, right, or if we have, a negative number plus a negative number, and, the answer becomes positive. So effectively what we say is, well, we say, yeah, if the two signs are the same, right, so yeah, if we have, positive plus positive, right, or negative but negative, but here, the answer is different, yeah, this is going to be an example of overflow. So, let's say the reason it occurred is because, well, here we've only got 8 bits, but yeah, that's not going to be big enough to represent the actual answer we need. So let's just say, right, let's say overflow occurs. And we could mention here about the signs changing. Let's say, yeah, overflow occurs maybe if, or let's say if 2 numbers of the same sign. Yeah, are added. Right, and let's say, yeah, and the result, becomes a different sign. So I think this is really more what overflow is, right? But if really we want to explain why it occurs, so I guess we can say, yeah, this occurs because, or maybe, yeah, this happens because. And what we want to say is, let's say there's not enough bits to represent the answer. Yeah, not enough bits to represent the answer. And I mean the reason for this, like of course if we were writing this on paper, I mean technically on paper you would never have overflow because you can just always add more bits, right? Always add more positions. But I mean let's say in a computer, well let's say a computer has a register or like ALU or something, and this is only 64 bits. Well, we can't suddenly like add an extra bit because like I mean this is literally the hardware. Of course the hardware only has like 64 wires, right? 64 half adders for example. So yeah, we can't just extend the hardware effectively. And this is same as denary, right? Because let's say we have denary 999 plus 1. Now if let's say we were only able to write 3 places, I mean then of course this answer, I mean if you were doing it kind of a 2's complement, I guess it would become negative. But of course if we're just writing it on paper, we can always just add an extra digit. But yeah, like in the computer hardware, right, of course we can't just add like extra space to the computer hardware, because yeah, I mean it's like a physical thing. Right, so 2, a student has a sound file that is too large to be stored on their external secondary storage device. The student compresses the sound file to make the file smaller. The compression method used reduces the sample rate and the sample resolution of the sound file. Right, so what's meant by the sample rate and sample resolution? So the sample rate, I mean this is just the number of samples per second, right, or the number of samples per unit time. Right, the number of samples taken, right, the number, right, of samples taken per unit time. And I mean for samples, we could also say that this is kind of a measurement of the amplitude of the sound. So yeah, maybe let's, I don't know, let's say here, each sample, let's say measures the amplitude, maybe amplitude or volume of sound. Because I think for these, if here it says sample, I mean, yeah, I think here, probably we can use sample again, it should be fine. But sometimes it is good, just to kind of explain what a sample is as well. Because yeah, otherwise you're just kind of explaining something almost recursively, because yeah, you're kind of explaining it in reference to itself. Right, so the next one, right, sample resolution. Well, this is just the number of bits for each sample. So let's just say that, yeah, the number of bits, right, so the number of bits used to store each sample. Right, okay, and I mean I think I do actually just have a diagram here just to demonstrate this. I mean, so this bit depth, okay, this is also the sample rate. It just means the same thing, yeah, bit depth, sample rate, 2 names for the same thing. Okay, bit depth and sampling resolution. But then here the sample rate, I mean the sample rate we can also call, the sample frequency or the sampling frequency. So you see, I mean, when we have, this first example here, we have a low sampling resolution. So here on the y-axis, right, also a low sampling rate, and then you see that's going to result in a large error, from, so let's say here, right, this one here is going to be the analog, and then the actual like digitized version that we've saved down here. Yeah, of course, this is not very accurate because, well, we're not taking the sound very often. The sampling rate is low. Likewise, we're not using many bits to represent each sample. So yeah, the sampling resolution is low, which means that, for example, I don't know, like maybe when we get to, I mean, I don't know, like let's say when we get to a position like maybe this one, we see really this is about, it's kind of in between, right? Whereas of course this will then have to get rounded down to this level. And as we see, like if we look at number 2 and then also number 3 especially, as we increase the sampling rate, right, and the sampling resolution, well then we're going to get less error, and again also less error here. I mean we're never going to get no error, because if you think basically an analog sample, well, it's just continuous. It's going to have like an infinite accuracy, or infinite number of decimal places, the precision. Whereas of course in a digital system, like we can never represent we can never represent an infinite precision. because we don't have infinite memory. Okay, so the next question says identify which type of compression has been used to compress the sound file. Right here it says, well, what they've done is they've reduced the sampling rate, right? Also, they've reduced the sample or the sampling resolution. So in this case, they've literally lost data because they've lost some of the samples, right? While they're reducing a lower sampling rate. And also they've introduced some kind of like rounding, right, or quantization errors because they've reduced their sampling resolution. So here then, this is going to be lossy. And some people, maybe they don't know. They think, well, how can we reduce the, file size of of like a sound file? Now you can just think back to the formula, and I mean the formula for a sound file. Well, it's going to be the, let's just say SF, or all right, well, let's go sample rate, I guess. Right, so it's going to be the sample rate. Okay, the number of samples per second. Right, then we want to multiply by, the number of bits per sample. So let's say here, well, that's going to be the sampling resolution. Right, let's say, well, the sampling or sample, I'm just going to go res. Now, this will tell us the file size for 1 second, right? So then we've got also multiplied by the duration. And then, we can also multiply by, well, the number of channels, so maybe not stereo, let's say channels. Because, for example, audio, I mean, a common one, you might have 2 channels. So you'd have like a left sound and a right sound, because if you have headphones, potentially you can have different sounds in the left ear and right ear. If you want some super fancy kind of like concert performance, maybe you'd have, I don't know, 16 channels or something, because you might have like 16 different speakers. So if we think about this, I mean, the duration you probably don't want to change. Of course you could speed it up, right? That's going to be one way to reduce it. But I mean, yeah, probably you don't want to do that. So you just think, well, either you can reduce the sample rate, right, reduce the sampling resolution, yeah, or of course you can reduce the number of channels, right, if there's more than one channel. Similarly, let's say for images, well, the formula, well, it's going to be the resolution, so the number of pixels, because the resolution is the width times height. Right, and then that's going to be multiplied by, well, the size, let's say the number of bits per pixel. So that's going to be the bit depth or color depth. And again, of course, because we're multiplying these together, well, either reduce the resolution, right, or reduce the bit depth. And yeah, that's going to be lossy compression. Right, so the next one, student sends the sound file to a friend. The file is transmitted across a network that uses packet switching. Identify 2 pieces of data that would be included in the header of each packet. Right, so if we think about this, I mean, a header, basically each packet, let's say this, the header, right, and I mean, here we could call it the data, right, often they actually call it the payload. So yeah, the payload is the actual like main data we're sending, and then the header, this is, I mean, basically it's like metadata, right, so extra data, that it can be used, for example, well, to route the packet across the network, things like, error correction or error detection. Things like checksums, right? But I think the main ones they usually mention, let's go, well, the source and destination IP. So I'm just going to say the source IP address. And I mean, usually, right, here we could actually write the destination IP address. However, possibly they might sometimes include both of these as the same thing. Because, of course they're different, but, they're still just IP addresses. So I think for me, rather than mentioning, 2 different IP addresses, I would probably mention something like the packet number. And if we think, well, the packet number, what this is used for is, actually, I think I've got a diagram here. So let's say we have, right, this is our network, and as we see, well, packet 1 has been routed, sort of here, then here, right, then obviously, yeah, finally at the destination. Packet 2 has actually gone this other route. But I mean, let's say, for example, I don't know, maybe here, like this router, this could have a backlog, right? So it could be really slow. So what could have actually happened is, well, packet 2 might have arrived first, and then packet 1 arrived second. And like probably you can tell, well, the reason you need a packet number is because, this receiving device, probably the network interface card, then needs to actually reorder those packets into the correct order. So of course then it's going to switch that into, order 1 then 2. We could also have a situation where, let's say we have, maybe packet 1 arrives, then packet 3 arrives. but of course, right, the network interface card is going to think, well, like, where is packet 2? So if it doesn't receive packet 2, well, then maybe it can send a message back, right, and then, you know, packet 2 can be resent. So yeah, that's just going to be two reasons, right? So reordering and also resending of packets that don't arrive. Yeah, that's why the packet number is required. So what we can do then, I mean, yeah, how the file is transmitted. Now, I'm just going to write in bullet points. However, for the exam, you want to be writing in paragraphs. So let's say first, probably the file is broken into packets. Yeah, right, let's say file broken into packets. I mean, maybe we could say small packets. Because, I mean, yeah, usually this would just be, you know, sort of kilobytes, right? They're certainly not going to be megabytes or anything. Right, so let's say the packets will be sent maybe sort of from router to router across the network. Yeah, I say packets sent maybe between routers across the network. Right, across, yeah, all right, let's say across network. Right, I mean, yeah, we could mention, let's say routers will use let's say routers will use a routing table in order to determine, you know, where to send it to. Right, so routers, yeah, use routing table. And I think here we can say, right, to determine next hop. Right, determine next hop. So I mean, a routing table, just to recap, like, let's say we've got, I don't know, like, let's say 5 different routers, right? They're going to have IP addresses. So let's say, yeah, I think I'm not going to have room there. Alright, so I think I'll draw it here. Right, so a routing table, well, it's just going to map, let's say, the destination to the actual IP address that we should send it to. So let's say we want to send something to, I don't know, you know, 100, like, I mean, it could be anything, right? 100.200.50.70, right? Whatever. But let's say we see something that starts with 100. It will then say, well, if the packet starts with, you know, 100, right, something, if it starts with, I don't know, maybe 200 or something, and, you know, this will be a range, maybe, let's say 200 till 220. The next one could be, I don't know, 221 to, you know, 230 or something. Well, then what it will say is it will then say, you know, send it to device number, I don't know, you know, 105 dot something something something. This one, it will say, right, if the IP address is in this range, it will then say send it to the router with, you know, IP address like 200, and then, yeah, whatever IP address that is. So effectively, we can just say, well, it's just going to map the IP. Well, it's going to map, let's say, the IP, you know, of the destination, right, to the next router. Yeah, I mean, hopefully that makes sense. I mean, if it doesn't, you can just go online, you know, type in like IP routing table, yeah, example or something. Right, okay, so yeah, they use routing table. Let's say maybe packets will be checked when they arrive. Yeah, alright, so let's say packets, I mean, we could say reordered, right, reordered when they arrive. Yeah, alright, let's say when arrive. Right, and let's say, yeah, and resent if they don't arrive. Right, so file broken into packets, packets sent, yeah, between routes. I mean, I think here when we say between routes, we could be more specific. So let's say, yeah, and it's a bit annoying because, you know, I don't really have space here. But we could just say, like, packets can travel across different routes. Right, so packets can travel across different routes in network. Right, let's say, yeah, different routes. And then, yeah, so we could mention, you know, the destination IP address is used to determine the next hop. I guess that's kind of here in this routing table. Yeah, I mean, I think for me that's probably enough. I mean, in the exam, right, maybe try and think of some extra stuff you can say. Uh, yeah, I mean, you could mention something like I don't know, maybe a checksum could be added, and you know, it's going to be recalculated at the end. Yeah, to check that there's been no corruption or yeah, no data loss or anything like that. So yeah, maybe let's just say checksum. Maybe checksum added. Yeah, before transmission. Although, to be honest, I don't think they would actually talk about checksums in IG, but yeah, you could mention it anyway. Right, added before transmission, maybe by sender. Right, and checked, or maybe, let's say, and verified. Yeah, by receiver. Okay. Right, secondary storage devices are used to store data in a computer. Right, circle three components that are secondary storage. Okay, well, so CPU, that's not going to be. Right, compact disk, okay, this will be. And if we just think secondary storage, well, I mean, when it says storage, right, this means permanent storage, right, so non-volatile. When it says secondary, well, this means not directly connected to the CPU, or yeah, can't be directly accessed by the CPU. Yeah, and so I mean that's really what we're looking for. So again, well, hard drive, that's also going to be secondary storage. I mean, RAM, okay, this is going to be, well, let's say primary memory, right, or primary storage, because yeah, RAM can be directly accessed by the CPU, right? Same for ROM, okay, this can also be directly accessed. But note the difference how RAM is going to be a volatile, yeah, volatile, you know, primary storage, whereas ROM is going to be non-volatile. And again, non-volatile means, well, when you turn off the power, right, the data won't be lost. Whereas, yeah, volatile, when you do turn off the power, right, the data will be lost. I mean, registers, again, well, these are sort of inside the CPU. And then, right, so SSD, right, that's going to be the other one. Right, so, yeah, which statement about secondary storage is correct? So, directly accessed by the CPU, well, no, because we said this is primary storage. Magnetic storage early, I mean, no, because, well, I mean, this could be like a hard drive, right, of course, also magnetic tape. But we also have, if we think the three different types, okay, we have optical storage, and then the other type, well, solid state storage, okay. So optical, that can be CDs, DVDs, Blu-rays, right, and then solid state, well, that's, yeah, solid state drives, SSDs, but then also, you know, USBs, right, flash memory, yeah, I mean, even RAM, actually, so RAM is solid state. Right, and then, so it's permanently store software and data files. Yeah, okay, so this one, right, and I mean, when it says permanently store, right, this just means non-volatile, whereas, yeah, volatile, this is the opposite. And, you know, again, right, some primary storage is volatile, right, so RAM would be volatile, but yeah, obviously some primary storage is not volatile, like ROM, right, or primary memory. Right, so complete, right, different types of software, okay, yeah, some terms will not be used, right, you should only use the term once. Right, something software provides these services that the computer requires. An example is utility software. Right, so if we just look, well, application software, I mean, I think not really. Right, assembly, no, this. So if we check these, I mean, I think probably system software. I mean, all right, so I'm just going to draw a line. Right, of course, in the exam you should write that. All right, well, let's just write it anyway. Yeah, because if we think, well, system software, I mean, that's going to include, I mean, well, things like the kernel, right? So those, you know, sort of fundamental, like important parts of the operating system. And that would be things, I don't know, I mean, let's say like file management, you know, memory management, things like, you know, connecting to Wi-Fi, connecting to Bluetooth, right? All of that is going to be the sort of important, you know, core operating system features. So yeah, that would be system software. Now, if we think utility software, I mean, these are not necessarily like as important, but you know, they're still quite important. And basically they're used for, let's say, the maybe we say like the smooth functioning of the computer. And yeah, you can kind of talk about efficiency. So utility, well, this can be antivirus, this can be like disk defragmenter. So if you have a hard drive and it gets fragmented, yeah, this can be, you know, defragmented to basically like to move all of the sort of same file, yeah, all of the parts of the same file, you know, just move them together. Right, also things like compression, things like disk checker, right, disk formatter, right, they would all be utility softwares. Right, next one, something software is run on the operating system, so I think this would be application. Right, then the next one, the something system is run on the firmware, which is run on the something. Right, so here then this should be operating system, because yeah, the operating system runs on top of the firmware. Yeah, all right, and then well, the firmware is going to run on the hardware. And if we think about this, I mean, let's say, well, the lowest level you've got the hardware, right? On top of the hardware you've got the firmware, because the firmware is going to be the low level software that directly interacts with the hardware. I mean, then I guess we can kind of say the operating system, although the operating system we can kind of break down into sort of smaller parts. So let's say like the low level parts of the operating system. I mean, I don't know, we can call this maybe like I guess we can sort of consider all of it really system software. Right, and then, I mean, the thing is, right, you can have some application software that's part of the operating system. But you know, you can also have, say, third-party application software that's going to be, sitting on top of the operating system. So yeah, I mean, I would say this, right, hardware is going to be the lowest, then you got firmware, right, then you got, you know, the operating system, and yeah, that's going to include, well, system software, right, sort of / utility software, then yeah, the application software is going to be on top of that. Right, so a farm has an automated drinking system for its animals. The drinking system has a water bowl that contains water. When the water bowl is empty, it is automatically refilled. Right, the system uses a sensor and a microprocessor. Identify the most appropriate sensor for this system. So if you're talking about, say, the amount of like water, or yeah, I mean, let's say, well, the amount of a liquid. I mean, probably the best one for this would be a level sensor. So if you think, let's say you have a cup, well, a level sensor is literally just going to measure, well, it's just kind of going to measure the height, you know, like what's the level of that water. I mean, you could mention a pressure sensor because, you know, you're going to be measuring the weight, right? Obviously the weight of that water. I think something like a flow sensor you wouldn't want to do, because a flow sensor is really like if the liquid or gas is traveling through like a pipe or, you know, through a valve. But yeah, I mean, in this case, you know, it's just stationary. So really, you just want to measure the, you know, the level, right, the amount of water. Right, then describe how the sensor and microprocessor are used to automatically refill the water bowl. Right, so I mean, usually there's always keywords that you say. They say like continually, maybe the sensor continually kind of, you know, measures the water level. So let's say that. Right, sensor, and again, you know, in the exam, write this in like full sentences, paragraphs. Right, sensor continually measures, right, water level. Let's say, I know, yeah, reading, or let's say, yeah, reading is converted by, because if we think, right, the sensor is going to measure, right, what's going to be an analog signal. So yeah, reading is converted, right, by an ADC. And let's put in brackets, right, so analog to digital converter. Right, so it's converted by an ADC into digital, maybe into a digital signal. Right, and sent to microprocessor. Right, then what we want to say the microprocessor will, basically it's going to compare this reading or this value, you know, with the kind of normal reading, right, or the normal kind of expected range. So let's say, or I'm just going to say MP, right, microprocessor, right, compares, let's say reading from sensor, or well, let's say, right, compares reading to, let's say, normal / expected value. Right, and then here, I mean, let's say, well, if normal do nothing, right, if normal, yeah, right, microprocessor will do nothing. And let's say here, what if the reading is too high? Right, if too low. Right, if reading is too low. And I mean here, you know, I guess it could get too high, like if it's been raining. but in that case, if it's too high, I guess you don't really have to do anything. Yeah, you can just wait for the animals to drink it. Right, if reading is too low, right then microprocessor. Let's say it will send a signal to an actuator. Maybe this can be it can like control a valve, and then I guess the valve will open in order to obviously like kind of opening the tap, right? Just to let more water flow in. Right, so then microprocessor sends a signal. And you could mention that this maybe sends a digital signal. Sends a digital signal to actuator. And we could mention here, signal converted to analog. So convert to analog. Using DAC. And in the exam again, probably in brackets, digital to analog converter. Just explain what DAC is. And then we could, I don't know, maybe we say like the actuator opens a valve to allow more water to flow in. Actuator maybe open, or wait, is it a pump? No, so it doesn't say. Maybe let's say opens a valve, or turns on water pump. Turns on water pump. To increase the water level. And then I guess you say, let's say when the signal, or when there's enough water, then it's just going to stop. Let's say when. Let's say when reading. Is normal. Let's say microprocessor sends signal to stop filling. Sends signal to stop filling the water. Alright, so I think that should be okay. Although again, these kind of questions, 6 marks, so I would say check the mark scheme. Have a look what they say. Right, next one, a user wants to connect their computer to a network. Identify the component in the computer that is needed to access a network. Now, notice here they're saying the component inside the computer. So they're not talking about the router or anything like that. So the component inside the computer, that's the network interface card. Let's just say that, network. I think, or you can call it network interface controller. That's also fine. Interface. Let's go card. And then in brackets we can just go NIC. Now, if it's for a wireless network, Wi-Fi, also I guess 3G, 4G, 5G. In that case you can also go WNIC, so like a wireless network interface card. I think let's just go network interface card, that's more general. Identify the type of address that's allocated to the computer by the manufacturer, which is used to uniquely identify the device. Now, because here, it's not talking about like when they connect to the router or something. It's talking about, sort of assigned by the manufacturer. So that's going to be a MAC address. And I think, we can put in brackets, that's what is it, media access controller or something like that. I would say check this. I think it's, I'm pretty sure it's media access. This controller I'm not 100% sure about. I think just MAC address is fine. And then if we just quickly look at the format of a MAC address, because sometimes they ask this. If we think like an IP address, it's going to be what? It's going to be 3 groups of numbers. Let's say another 3, dot, another 3, dot, another 3, dot. That's going to be IPv4. So for IP version 4, you say it's going to be 4 groups of 3 denary digits. Not necessarily 3 denary digits, because you could have something like 7. But you say it's going to be 3 groups of numbers in the range 0 to 255. If we want to think about IP version 6, and I guess you can say in total this will then be 32 bits, the whole thing. IP version 6, that's going to be 128 bits, and here we're going to have 8 groups. I think for when they mention this, you'll say IP is separated by the dot. Right, but for IP version 6, there's going to be 8 groups, and each group is going to have 4 hexadecimal characters, or 4 hexadecimal digits. And here we can say, well, either they're separated by the, I think actually always they're separated by the colon. So you might have something like, I don't know, like 1111, then dot dot, I don't know, maybe 00, like F4. But then the thing with IP version 6 is that if, for example, we have something like 0000, then, you know, another like group of zeros like this, like basically this we can just shorten. So in order to represent that, we can literally just do, so we've got the dot dot here, right, the colon, and then the other colon here. And then, for example, if we have, I don't know, maybe we have another group, another group, another group, another group. So let's say here, if we had 7 groups, and then just one empty, well, then we would know, right, there's only going to be one group of zeros that's in this place. But let's say, for example, I don't know, well, I mean, here we've got 2 groups. Let's say here we've got, I don't know, maybe another 3 groups. Well, because we need 8 groups in total, you know, that would tell us that actually there's going to be 3 groups of just all zeros. Because if you think, well, we've got 2, right, and then we've got another 3, so that's 5. But of course we need 8. So it must mean that, in this, in this gap here, there's going to be 3 groups of all zeros. But then just going back to a MAC address, well, a MAC address is going to be, 12 hexadecimal digits. So I mean, maybe like AA, let's say, BB. Right, and then let's go, for example, I know, 1, 2, right, 3, 4, 5, 6. So what we say then, the first 6 are going to be assigned by the manufacturer. And you can literally go online, let's say if you find your, let's say you find your MAC address for your network interface card. And I mean, you can easily find this in like your system settings or commands. And then you can type that in and it will tell you, what manufacturer made this, okay? Because again, these 6 digits correspond to an actual sort of manufacturer and model. I mean, the next 6, they're going to be unique for your particular device. And actually for a MAC address you can use 2, right? So a MAC address can either use the colon, or it can also just use the hyphen like this. So, let's say like AA, right, hyphen, BB, obviously, etc. So either hyphen or colon is fine. Right, so anyway, the next one then, right, dynamic internet protocol IP address is allocated to a computer when it's connected to the network. Right, identify the device on the network that can connect multiple devices and automatically assign them an IP address. So like this one is a little bit confusing because I think when it says connect multiple devices, I mean this sounds like a router, but then when it says automatically assign them an IP address, well, this sounds like DHCP. Right, well, so DHCP server. So DHCP, well, right, dynamic host control protocol. And what this does is, let's say your router has, I don't know, let's say like 253 available IP addresses. Because, for example, I think some are reserved. Like I think 0 you can't use. I think 1 possibly you can't use. Then I think others like 255, right? You also can't use. So I don't know. Maybe you have like 252 that are available, or 253. Well, what the DHCP server is going to do is it's going to check which of these IP addresses are, which are already being used by someone else, and then it's going to give you one that's not being used, right? So effectively, it's just going to store a table of which IP address is being used. But the thing here, because it is kind of talking about both of these, right? It's talking about a router and DHCP. So I think for here, right, this is why they actually say router as the answer. Because let's say like a home router actually does many functions. I mean, obviously it operates as a router, and I mean a router, all that does is it just sends, basically it just sends packets onto the next hop. Again, based on the IP routing table, right, or just the router's routing table. But then, I mean, we think, well, it also acts as a DHCP server because it's going to assign you an IP address, when you connect. Right, a home router is also going to act as a DNS server. Right, it's also going to be a gateway. So a gateway, that's going to allow communication between different protocols. I mean, it's also going to act as a switch, because a switch, well, we can connect like an Ethernet cable or a twisted pair cable. And then I suppose, well, it also acts, I mean, let's say it acts as a, let's say, right, so wireless access point. Yeah, I mean you can call that right WAP, but yeah, I guess just wireless access point, right? That's going to be the whole thing. So we see that a home router actually does many functions. Right, so the next one will describe what is meant by a dynamic IP address. Yeah, I think I don't have much space here. Right, so dynamic, we could say, well, this will be, I mean, this is basically what we said. So let's say maybe an IP address, maybe temporarily assigned. Yeah, okay, so let's say, yeah, alright, so yeah, I think temporarily is okay. Right, and I mean, that's going to be assigned by the DHCP server. Right, so yeah, by DHCP server. And again, like for a home network, well, the DHCP server is going to be included within the router. Right, so I think that's probably 1 mark, or yeah, maybe 2 marks. I mean, we can say, let's say when they turn off their device, after, let's say after a certain time, if they've not renewed it. So, okay, let's say this. So, dynamic IP addresses have to be renewed. Yeah, so let's say that, right, so have to be renewed. Right, have to be renewed, right, otherwise maybe will expire and can be used by other people. Yeah, will expire. Right, yeah, let's see, right, and made available. Right, made available. Right, to other devices. I mean, I think that's okay. I mean, since it's an IP address, maybe just to make sure we hopefully get the 3 marks, we could just say has to be unique for that network. Yeah, I said, well, let's just say, right, is unique. Yeah, well, let's say, yeah, for that network. I mean, if it's public, right, then it's going to be globally unique. If it's a private dynamic IP, well, then it's only going to be unique on that network. Because you can have, let's say, 192.168, I don't know, .0, I don't know, let's say 100. Now, right, other people can also have this IP address, right, but not on the same network. Yeah, so that's the thing, right? I mean, private are going to be unique, right, but only on that, only on your network. Yeah, I mean, that should be fine. I mean, this thing about, IP addresses expiring, like, basically, when you connect to your router, or yeah, when you turn on your device, I mean, the router will assign you that IP address for a given amount of time. Let's say, for example, maybe it's 8 hours. Now, what's going to happen is, well, after half of that time, so after 4 hours, so I'm not sure if it's your device that contacts the router or if it's the router that contacts you. I think probably it would be your device that would contact the router. And basically it's going to say, well, yeah, can I extend this license, or can I extend this like lease, basically, because yeah, I mean they call this the lease time. And if the router says, yeah, okay, that's fine, like yeah, fine. I mean, then it's just going to extend that, so I don't know, maybe adds another 8 hours or something. However, let's say if for some reason the router says no, or you can't connect to the router, well, then it's going to half the time again. So, I mean, first we waited 4 hours to check, right? Then we're going to wait 2 hours, so we're going to half. So yeah, then we're going to check after another 2 hours, which I guess, the total time elapsed, right? That's going to be 6 hours, because we've waited 4 hours, then another 2. Right, again, if that's also unsuccessful, it's then going to wait another half, so it's going to wait 1, right? Then obviously 30 minutes, 15 minutes, yeah, 7.5 minutes, etc. So kind of like radiation, it's like a half-life, just keeps halving each time. Right, the next one, a program uses a low-level language to write a computer program for a vending machine. Describe what is meant by a low-level language. So I think first, well, we can say it's a language that's close to the CPU. Yeah, so all right, let's say language close to the CPU instructions. Right, so we could, yeah, I mean, we could say it uses kind of short, simple instructions. Right, short, right, simple instructions, or mnemonics. Right, so mnemonics, is that maybe N, M, or yeah, maybe M, N, I'm not sure. Yeah, something like that. Right, I mean, we could mention maybe just examples. So let's say, right, assembly, right, assembly and machine code, right, are low level. Yeah, I mean, I think that should hopefully be enough for 2 marks. Right, okay, so give 2 reasons why the program would choose to write the computer program in a low-level language instead of a high-level language. Right, so one, you can say, well, the performance could be... Alright, so I mean, if we look at the main advantage, I guess you can say, well, you can directly access the hardware. For example, the registers. So yeah, let's say that, let's say you write, and again, in the exam, try and write this a bit more formally. Yeah, I'm just kind of doing it short. So let's say directly access hardware. So yeah, let's say e.g. registers. Right then, another example, I mean, we could say performance, because possibly it's faster and possibly you can also use less memory compared to if you were using a high-level language. Now, this really depends because if you think, right, when you write a high-level language, well, if it's compiled, then the compiler is going to be converting that into machine code. So effectively, what you're asking is, well, is the assembly that you can write as a human, faster and more memory efficient than the machine code that the compiler can, produce? And in many cases, it's probably not, right? In many cases, the compiler will actually be, a lot better than, humans, to be honest. So I mean, let's just say possibly, right? So possibly can produce, let's say, more efficient code, or more efficient programs. Right, programs, and let's say, right, in terms of speed and memory. Right, okay, speed, and let's say, and memory usage. And I think, I mean, I did actually, so I do have some examples of some optimizations that a compiler can do, right, just to give an example. So one common one, in fact, hang on, let me just zoom in a little bit. And I'll just move that across. So one thing you can actually think, right, let's say we have something like multiply by 17. Now, multiplication, right, and well, divisions especially, right, they can be quite slow. So, and I mean, there's actually a website, I think it's godbolt.org. And yeah, this is a good website where you can actually see the machine code that the compiler will produce. And I mean, actually here, this website, this will actually display it as assembly, right, just so it's more human readable. But I mean, it's interesting because, well, you can see like what optimizations the compiler has actually done. But let's say, for example, here, like if we have 17, well, rather than multiplying by 17, we can actually do something like a logical shift left. And so this is an assembly instruction, right, a logical shift. And hopefully you know that, again, well, if we shift left, we're just going to be doubling. So let's think here, like if we shift left 4 places, so let's just do, let's just do that. So we're going to shift by 4 places. And this is kind of like Cambridge assembly syntax. So right, if we're shifting left by 4 places, I mean, that's the equivalent as doing, right, multiply by 16. But here we want to multiply by 17. So then in order to do that, right, then we can literally just go add 17. So yeah, doing this logical shift left of 4 and then adding 17, right, these 2 instructions combined is going to be the equivalent of multiplying by 17. So again, I mean, the compiler is definitely going to do this kind of thing. And you can see this on, godbolt.org. But for humans, humans are probably not going to do that, right? They're just going to multiply by 17. And then, I mean, there's other ones like constant folding. So constant folding, and right, for IG, you don't need to know this, but yeah, maybe some people are interested. Right, so constant folding, this just means, well, if we have some expression, and right here there's only constants, so we can actually pre-compute this value at compile time. So rather than doing 10 times 17 as the program is running, well, yeah, we can just calculate that in advance as being 170. And in that case, we're not having to do the multiplication as the program is running. And you know, this can also be optimized further. Like let's say we're not using this x anywhere else. Well, we could then literally just rather than outputting x, we could literally just go output 170, and then you know the program potentially could actually delete that declaration, like if we're not using that anywhere else, and yet it can just directly output 170. And so some of that, I mean, it's also, well, yeah, let's say dead code elimination. Right, that's another word for, well, yeah, just removing the code that's not necessary. Right, something like loop unrolling, what we can see is, well, here we're having to loop 10 times. And in assembly, what's happening is, well, first we're obviously assigning 1 to n. Right, then we're gonna, well, yeah, then we're gonna output this n. Right, but then when we get to the end of the loop, well, basically you're doing kind of like an if statement. You're checking, well, yeah, is the value of n, you know, sort of what, less than or equal to 10? And if it is less than that, right, then you're going to jump back to this 7. So effectively, there's actually quite a lot of instructions because you're doing an if, you're doing a jump. Well, also you're going to be doing an increment as well. Whereas effectively, what you can actually do is, well, rather than having the loop, effectively you just go, you know, output n like this. And you know, you could do sort of like output n right then, yeah, sort of n plus 1, n plus 2. Although potentially the compiler will actually literally just go, yeah, output 1, output 2, output 3, because you know the compiler can figure out what your code is doing. And then the last one, something like function inlining. Again, likewise with a function, when we call this, well, first we're having to do things like we're going to be adding these parameters to the stack, we're adding the return address to the stack, we're also having to jump to another part in memory. So yeah, all of that, right, it's going to take a little bit of time. So rather than actually doing that, you can literally just copy this code. So effectively, right, just deleting this function. And then we're just going to directly kind of replace the function with the actual code. So in that case, we can literally just directly output that. And again, so that's why I say, like, possibly a human can, you know, make faster code than the compiler. Right. However, in many cases, because the compiler is doing all of these optimizations, to actually make something that's better than the compiler, I mean, honestly, you'd have to be like an expert in assembly, really, to, you know, sort of make something better than that. But anyway, if we go on to the next one, right, a manager at a company is concerned about a brute force attack on its employee user accounts. Right, describe how a brute force attack can be used to gain access to the employee user accounts. So, I mean, this is basically trying every password, right? Trying every combination. So, all right, let's say, yeah, brute force, right, involves, let's say, right, attacker. I mean, like, let's assume maybe they know some of the user accounts, or yeah, maybe they don't. I mean, if they don't, to try every combination of user account and password, I mean, there's going to be like, yeah, just a huge number. Alright, but let's say, yeah, trying combinations, well, I mean, not necessarily all combinations, but let's say, yeah, all / many, yeah, combinations, right, of, let's say, username, right, and password, yeah, maybe until successful, yeah, or until hopefully successful. Right, however, you can imagine this is obviously not going to be very efficient. And you can think, like, let's say, you know, a lot of websites and things, they say, well, a password should be 8 characters. Now, let's say a user is just selecting from the set of, well, uppercase, lowercase numbers, and then maybe, let's say, 10 symbols. So you can think of that, well, uppercase, well, there's 26. Lowercase, there's also 26. Right, digits, there's going to be 10. And let's say maybe 10 common symbols. Like, well, you know, exclamation mark, the at symbol, right, question mark, whatever. So I mean, that's going to give us, what, 52, 62, right, 72. So if you think, right, if the password has a length of 8, well, that's going to give us, right, 72 to the power of 8 different combinations. And I mean, yeah, that's going to be some huge number. So brute forcing all of that, I mean, it's just going to take so much time. But you can probably think, you know, most people are not going to use a password, let's say exclamation mark, like maybe at symbol or pound symbol. Yeah, let's say the at symbol, I don't know, question mark, you know, something like this. Right, you know, people, they generally don't use these. So what you can do, you can have something like a word list, which is going to contain like a list of, say, all of the words in the dictionary. And then you can try sort of these combinations, because maybe someone, they have a password, I don't know, like, you know, Alan123. because, you know, let's say, well, their name is Alan, for example. So yeah, you could say, I mean, well, let's say attacker. So right, attacker could use word list. Or let's say word list. Yeah, maybe slash like maybe or let's say like any known personal information. Because if they're doing like some sort of targeted attack, right, maybe they know the name of this person, or they know the name of their city, or they know the name of their I don't know, the name of their pet or something. Right, because yeah, often people use, you know, passwords that contain these sort of personal information. Right, any known personal info, yeah, to speed up brute force. Right then, is there anything else we can say? I mean, not really. I mean, you could say that, I don't know, like a brute force is a simple attack, but of course it's going to be quite obvious. It's going to be, I mean, it's going to be obvious for people like, I don't know, someone looking at the logs, because, you know, they'll be checking someone seeing like, you know, billions of requests trying to log in. So yeah, maybe you could mention that like it's not a stealthy attack. And then yeah, maybe sort of like heavy-handed / not stealthy attack or something like that. Although here they're saying describe, so I think yeah, that's not really relevant for describing. Right, so one possible aim for carrying out brute force is to install malware onto the company network. Right, state two other aims for carrying out a brute force attack: to gain access to the employee user accounts. Right, so one, I mean, maybe they want to steal company information. So we could say like spying / yes, stealing company information. Right, company info. I don't know, yeah, e.g. like trade secrets, or yeah, copyright material. Yeah, or well, I guess like yeah, intellectual property. So let's say yeah, IP. But of course, yeah, in the exam, write intellectual property. I mean, the next one could be financial, right? Maybe they want to hold the company hostage by, I don't know, you know, deleting data, encrypting data, yeah, threatening to release information. So let's say, right, financial. Yeah, and we can say, right, yeah, e.g., let's say ransomware. Yeah, like, I don't know, maybe I guess we can say blackmail. So blackmail in terms of yeah, threatening to release information if they don't give you money, right? Something like that. And again, in the exam, you know, just like if you've got 2 lines, right, then just explain on those 2 lines. Right, so identify 3 types of malware that could be installed. Right, I mean, so let's try and list all of them. So first we can say spyware. And spyware, I mean, as the name suggests, it's going to be spying, right? So it's trying to find, I mean, basically it's trying to find information, right? It could be username, passwords, yeah, it could be intellectual property, right? Credit card numbers, email addresses, telephones, or anything. I mean, the next one, I mean, we could say ransomware. So ransomware, what this will do, I mean, usually it's going to encrypt the files, you know, it could also delete files. But basically it's just going to ask for money, right? It's going to ask for a ransom. And if you pay the ransom, if you pay the money, well, then they'll give you the decryption key. And with the decryption key, right, then you can, you know, well, then you can like decrypt your files, yeah, get them back. I mean, yeah, I guess you can say virus. So a virus that's just going to spread, well, it's going to spread to files on that one device, right, on that one computer. I mean, better than a virus is if someone can make a worm, because a worm is actually going to spread onto different computers. And I mean, you think, right, I mean, the way they're called this is quite kind of like self-explanatory, because if you think, well, in a virus is just going to multiply, you know, kind of within your body. You know, it's going to infect one cell, then it's going to spread and infect another cell, right? Whereas something like a worm, I mean, if you think, let's say this is the ground, well, maybe a worm, right, it might go into the ground in this position, right? It's then going to sort of burrow under the ground, and then, yeah, maybe it then reappears in the ground in this position. And you can think, I mean, like, let's say here, right, this is, yeah, computer 1, right, then it's going to reappear here on computer 2. So that's the thing about a worm, right, it's just kind of burrowing in and, yeah, infecting all the devices on that network. Right, you can mention something like a Trojan. or yeah, well, Trojan horse, just Trojan. So what's that going to be is, let's say you have an executable file. Now you can have the normal executable, let's say just the data, right? So it's going to be fine, it's normal. But then you can add like a malicious, let's just do like an X, right? So this X is like the malicious code. So let's say you say, hey, here's like Microsoft Office, and yeah, I know you send that to them. Now for them, they can run that, and because you've got the normal code, well, it's just going to open like normal. It's going to be Microsoft Office. But sort of unbeknownst to them in the background, right, it's also going to be executing this malicious code. And I mean, the reason it's called a Trojan is, well, the Trojan horse, and yeah, people can search this story. I think it's, what was it, maybe Troy or Sparta, or yeah, I know the Greeks. Basically you had soldiers, they were hiding inside this horse. It was like a wooden horse, right? I think, well, one army, they gave it to this other city as a gift, but then like when everyone went to sleep, well, the soldiers, they then exited this horse, just killed everyone in the city. Obviously took over. And I mean that's why they call it a Trojan, right? Because again, you've got the normal file, so it looks fine, but then yeah, like hidden, you've also got this malicious part hidden inside. Right, so spyware, ransomware, virus, worm, Trojan. Yeah, so what am I missing? I mean, so things like spyware, this can also include things like keyloggers. Yeah, I mean, I think that's the main ones. I mean, other people can probably remember. I think there's one or two more. Yeah, my memory is just terrible at the moment. I mean, if you want to know the other two, just look in the book. Yeah, find out what those are. Right, so give 2 security solutions that could be used to help prevent a brute force attack being successful. Right, so here, I mean, you can limit the number of login attempts. Right, yeah, limit number of login attempts. And maybe like say, and provide lockout, or yeah, kind of like a time limit maybe. Or yeah, maybe and time delays between login attempts. Because for example, if you think your phone, right, let's say they give you like 5 login attempts, right, let's say LA for login attempts, and right, let's say if you're unsuccessful for all of those 5 times, well, then what will happen is it will say wait 1 minute, right? Then if you try again, if you're unsuccessful again, right, then it will probably say wait 2 minutes or wait 3 minutes or something, and of course the time is going to keep increasing. And you might think, well, that's good, right? It prevents someone hacking you, or yeah, using brute force, which is true. But people have actually used this as a malicious way, because let's imagine you see someone's phone like on there, just on the desk, and like maybe you want to play a prank on them, right? Or it could be important, right? Maybe they need to make an important phone call, or yeah, maybe they need to use it to scan some QR code to like access someplace. Like you could deliberately use incorrect login details, right, to deliberately lock them out, and maybe to time them out for 60 minutes or something. Yeah, in which case, of course, well, they can't access their phone. Right, but if we think another one, so how could you prevent a brute force? I mean, you can probably just mention something like, I mean, you could probably mention a firewall, because with a firewall you can of course monitor the amount of requests. I don't think you want to say antivirus, because again, this is going to be coming like sort of externally. So it's not malware that's already on your system, right? So you can't really detect it with antivirus. So let's say firewall. Yeah, maybe, I don't know, like to limit traffic from a specific IP or something. Yeah, maybe specific IP. Now, of course, if they're sophisticated, they could get around this with some kind of botnet. But again, yeah, that's going to be much more advanced if they're kind of wanting to do that. Right, company uses robots in its factory to manufacture large pieces of furniture. One characteristic of a robot is that it's programmable, right, to state 2 other characteristics. Yeah, of a robot. So the way I remember this, I think just PEM. Of course, you can change the letters, maybe MEP. But yeah, I think PEM, right? So, well, P, right, that's programmable, All right, E, so it's going to be electronic. So that's like electrical components. Yeah, M was going to have mechanical components. So let's just say that, right? Well, I mean, let's say contains. Yeah, contains electronic components. And I think the next one I won't write, but I mean the next one you just want to say what contains mechanical components. And you can probably give an example, like mechanical can be an actuator. Yeah, electronic components, maybe you say, memory, storage, like a hard drive, right, CPU, microprocessor. Right, give 2 advantage to the company employees of using robots to manufacture large pieces of furniture. Right, so for employees, I mean, you can probably say it's kind of like less tiring. Because I guess, yeah, manufacturing furniture, I don't know, maybe they're having to saw, they're having to, hammer, stuff like that. So yeah, let's say less tiring. Yeah, let's say less tiring for employees. And then probably you just want to explain this, right, since they don't have to do, or maybe, yeah, since robots can do the physically demanding jobs. So let's say, yeah, do physical tasks. And then, I mean, yeah, maybe you can mention safety, right, safety improvements, because again, the robots can do the dangerous tasks. So yeah, all right, robots do dangerous tasks. Right, so give 1 disadvantage to the company owners who are using robots to manufacture large pieces of furniture. Right, so probably here, I mean, let's say high initial setup cost. Right, so let's say, yeah, initial setup. Yeah, I think that's fine. Because I mean, setup also includes purchase, really. You could say, requires maintenance, because if the robot breaks, it needs to be repaired. Yeah, maybe if the specifications change, right, you want to like design a new piece of furniture. Of course, you then have to program the robot to design this new piece of furniture. Yeah, you can also mention if the robot stops working. Maybe the robot, because robots are fast, right, of course they can start producing like huge numbers of kind of, let's say, faulty furniture. Whereas like a person, of course a person can detect, if they sort of produce something that's like, yeah, not good. Whereas if, say, the quality assurance part of the robot kind of fails, then maybe it's going to be passing furniture that should actually be, being rejected. Yeah, because it's like failing the tests. Right, so students use the internet for their schoolwork to research what is meant by pharming, right, state the aim of pharming. Okay, so pharming, I mean, basically this is used to, steal user credentials, or yeah, maybe steal information. Right, to steal, steal user, yeah, let's say user information, and then probably give an example. Right, so yeah, e.g., right, usernames, right, let's say passwords, right, yeah, PW, then what, credit cards, which I think is CC, credit cards. Yeah, obviously in the exam, write that in full. Right, draw an annotated diagram to represent the process of pharming. Now, this question to me is really weird because when most people say pharming, I mean, they think of, let's say someone set up a fake website, and well, first you have phishing. So phishing is, sending them a sort of fake email. And yeah, I don't know, maybe the email can come from like, rather than say google.com, I don't know, maybe like Google, and this is like a 1, right, e.com. And so of course people look at this quickly, and they don't notice that it's actually a 1, not an L. So yeah, they go there, they then type in their Google like email and password, right, and then of course people have stolen that. So like the first part would be phishing, where phishing is like sending them the fake email or the fake text, trying to impersonate someone else usually. And then pharming, this is the actual kind of second stage, right? So this is the process of actually stealing the data by creating, the fake website. But yeah, I mean, here they're not really talking about that. They're more talking about what's something called DNS spoofing. Because yeah, for this one, or I mean, well, not, I guess DNS spoofing. Also really DNS cache hijacking. So this is where, for example, you can change the DNS record so that rather than directing to the real google.com, it's actually going to redirect to your like fake google.com. which again, this could be google1.com or something. And then, of course, now the user is on the fake website. Of course, they're going to type in their details. So yeah, let's try and mention something like this. So let's say here, this is like the client. Let's say client, or maybe user. Right. Let's say the DNS server. All right, DNS server. Right. So what's going to happen then? They're going to send a request to the DNS server. But let's say, right, DNS server has been compromised, maybe. So yeah, maybe the DNS server has been hacked. Let's say, I don't know, yeah, now or it has invalid or incorrect DNS records. And I mean, let's think about what DNS records mean. So let's say you have a table like this. And basically you're going to have, well, it's just going to map what domain names to IP addresses. So let's say like google.com. And I don't know, I mean, let's say Google has the IP like 123.123.123.123. So, I mean, this is going to be like the real IP address, let's say. But, and so what you do, right, okay, you send a request to the DNS server, and, your request is, well, what is the IP address of, google.com, right? And then the DNS server will then send back the IP address. So, like 123, whatever. However, if somehow someone has managed to like hack the DNS server, and they've managed to modify this, right? Then of course it's going to send back this incorrect IP, and yeah, that's then going to redirect you to this kind of malicious website, right? The malicious web server. So yeah, we just kind of want to mention that. Yeah, I mean, so let's kind of do that again, right? So we say like Google, right? Yeah, google.com. Let's say right DNS request. So probably in the exam, right, yeah, DNS request to google.com, and let's say here, I don't know, maybe 222, yeah, whatever, and let's say, right, this is the invalid, or yeah, let's say the invalid or malicious, web server, let's say, right, malicious IP, or well, let's say, yeah, IP of malicious site. So, well, then what's going to happen, right, the user, then they're going to go to this. So let's see, well, this is the server or web server. All right, yeah, so right, okay, web server. And this will be the web server, like 222, of this malicious IP address here. So right, yeah, then it's going to go to this one, right? This will then send back the page. So let's say, right, send HTML or send web page. And then we can say, well, the user, basically the user is then going to type in their details. So maybe user, right, sends information or sends personal details. And then, so here we can say, let's say, right, web server, right, let's say, yeah, now stores the compromised user details. Yeah, let's say stores user details, right, that should be fine. Yeah, so hopefully that makes sense. So what's going to happen again, I mean, this DNS server here, right, this one, this has been compromised. So when the client sends a request, it's going to ask, well, what is the IP address of google.com? The DNS server is then going to send back, this incorrect, right, IP address. Right, the client, so the web browser is then going to send a request to that IP address. But of course, this IP address is of the malicious web server. The web server then sends back, let's say, the pharming page, which could be, yeah, like the fake, Google login page. And then because the client thinks it's real, because actually for them in this case, I mean, if they go to their address bar, right, their address bar will literally say google.com. Like it's not even going to say like, Google one, because I mean here, like it, I mean basically it genuinely believes that this 222 is the correct IP address. So yeah, right, this is going to say google.com. So I mean for the user, this will look 100% legitimate. Of course, then they'll then type in their username and password, right? Because they obviously trust it. And then, yeah, the web server is then just going to save that. And of course, the hackers can now use this to try and log in, say, to the real Google, using these details. Right, so next one, the student uses a web browser to access data on the internet. Explain the purpose of a web browser. Right, so I think you say, basically it's going to send, let's say, send requests or send HTTP requests. Yeah, I know, maybe like, let's say format and send. Right, so format and send HTTP requests. And let's put in brackets, right, S, because it could be HTTP, right, or yeah, HTTPS. And well, the S just means secure. So if it's HTTPS, it's going to be encrypted. Right, if there's no S, right, then it's not going to be encrypted. But right, so it's going to format and send HTTP requests. Run, yeah, let's say maybe and listen to response. Right, yeah, and listen to response from server. Right, so when it's then got a response from the web server, then we can say, yeah, render the web page. So let's say, yeah, render, HTML, yeah, I don't know, CSS, right, execute JavaScript, right, etc. Yeah, to display the web page. Right, so I think that should be fine. Right, storing cookies is one function of the web browser. Give 3 other functions of the web browser. So we could say like maybe page navigation. Right, so let's say page navigation. And when I say navigation, I mean like the back button, the forward button. So yeah, just mention that. Let's say right back/forward buttons. Yeah, I mean, I guess similarly, we can also mention like stores history. So let's say stores history, right, of previously visited pages. I mean, the next one you could mention, for example, like bookmarks, favorites. Yeah, so I think, I mean, they would probably be about the main ones. Yeah, because I mean, obviously cookies they've mentioned, right? I mean, things like here, sort of formatting and sending the requests, right? We've kind of mentioned that already. Rendering the page we've also mentioned. So I think, yeah, maybe don't mention that again. But I think maybe it'd be okay, right? You say, it's going to communicate over the HTTP protocol, yeah, with a web server, right? Something like that. Right, so is this the last question? Yeah, okay. Right, so a student visits a website that uses session cookies instead of persistent cookies. Explain the difference between session and persistent cookies. Right, so let's say session cookies. Right, so these are only going to be, I mean, you can say let's say they're stored in RAM. So yeah, okay, right, stored, let's say stored temporarily in RAM. Right, and let's say, yeah, and will be lost. Right, so yeah, will be lost when user, closes the browser, turns off the computer, right, so when they kind of leave their session. Right, when user, yeah, I mean, let's just say like kind of closes browser. Because, I mean, obviously turning off the computer, right, is also, closing the browser. But I mean, let's just mention them specifically. Maybe turns off device. And then I think maybe we can just mention the kind of things stored in session cookies. So it's just used to store temporary information, which I guess we've kind of mentioned that. Used for temporary, yeah, let's say info. Right, e.g., right, let's say e.g. shopping cart. Maybe things like their current comment or something, or current, I don't know, maybe current input on page. Because if you notice now, a lot of websites, I mean, certainly the sort of more popular websites, let's say if you're like writing some, long comment or long post, right, it could be on Discord, it could be on, yeah, I don't know, on YouTube, on, Facebook, whatever. Let's say, for example, if, I don't know, like let's say the internet just drops off. Yeah, or maybe if you kind of, I don't know, there's some error, which the page closes. Well, if you reload the page, and I think Discord might have this feature. Well, if you reload the page, then, your comment is going to be saved, right? It's going to reload that comment automatically. And, one way is where it can be stored in like a session cookie. I mean, technically, right, web browsers, they actually have, more different types of storage. But yeah, if we just want to be simple, we can say, right, it can be stored in a session cookie. Yeah, although in reality it probably wouldn't, right? There's actually kind of better types of storage rather than cookies. Right, so let's go persistent storage, or well, persistent cookies. So we say, well, these will be stored, I mean, they're not permanently because they do have an expiry time, but let's say, right, stored, yeah, for a given time. Yeah, and we can give an example, I know, e.g. 6 months. I think they say 6 months is the limit, and if you're sort of storing this for longer than 6 months, I mean, if it's storing any sort of personal information, right, then potentially you can get into trouble because, sort of privacy concerns, stuff like that. Yeah, that's why you always have those annoying, like accept cookie messages on the websites. Right, stored for a given time. Yeah, let's say, right, and won't be deleted. Right, and won't be deleted if user closes their browser. However, you can delete them, if you go into your history and go like, yeah, delete all cookies, delete history, all of that. So we could say, let's say used for, and then we want to think, well, what might a website want to store permanently? So, I mean, it could be, for example, their username. Yeah, all right, for permanent, or yeah, things we want to store permanently. Right, let's say e.g. like could be username. It could be things like site settings, so maybe you choose a certain language. Well, let's say, I don't know, you choose like sort of Arabic or yeah, Russian or French. Like you wouldn't want to log into the website again and next time it goes back to English. So yeah, maybe like site language. You could say like sort of, dark mode, light mode, yeah, any other kind of site settings, right, stuff like that. Yeah, I'm sure you can think of many examples. Right, guys, so I think this video went on super long. I mean, I did try and explain things in detail. This is almost like covering these kind of mini chapters, in the actual exam, or yeah, in this, past paper. Now, hopefully that's useful. And again, because, if you just want to see the answer, well, to just see the answer, you just look at the mark scheme, right? So the whole point is, yeah, I'm trying to explain in more detail. But anyway, right, if this is useful, we'll hopefully see you again in the next video.